那我不说话了。好的，我对准了，在这个屏幕上写。
那我就先写这个，我先写这个，然后客厅要跑出去搞点事。
Okay, perhaps this is a good time to get started. So, welcome back, and I suppose we have very nice and warm spring festivals. And well, actually, I can notice that there are some people missing it. Probably that's still on the vacation, which is understandable, right? And so please don't forget to submit your homework too. Okay, we also got 2 weeks of homework too, right? Before Wednesday, and before Wednesday midnight. Okay, and from now on, all the deadlines are going to be strictly enforced, and the emails will not be accepted anymore. And so I just checked our Albert. It seems that our final is scheduled on May the 15th. Is that right? So our final is scheduled on May the 15th. Probably I can't exactly remember if that is the same time, but probably it's the same time. So May the 15th is our tentative final date. And please schedule if you have international flights or other schedules. Please schedule that according to our final schedule. And so these are the logistic stuff, and we'll be starting with chapter 2 for now. Okay, and so I have just printed our class roster, so that will make me able to call your names directly. Okay, to familiarize myself more with these forms. Okay, so let's try to recover what we have discussed in the last session. And in the last part of the last session, we actually got into how to solve the wave equations in a very general manner, right? So imagine that we're having something like UTT equals to c squared uxx, and let's just say for now that our wave equation is defined on one dimension and on the whole real line, which means that from infinity to positive infinity. Okay, and c of course is the wave speed. Okay, c is the wave speed. I guess I don't need to convince you again, right? Why c is wave? We have derived that for several times in different ways. Okay, and so this can be rewritten into something like utt minus c squared uxx equals to 0. And if we are willing to write it down in the sense of the operative form, okay, then we can derive it. We can write it down as something like partial tt minus c squared, partial xx, this linear second order differential operator action upon u, and that brings u to 0. Okay, and that's simply that is very directly that actually straightforwardly speaking that. Okay, so let's say u again. Imagine that u is a vector. Imagine that if u were a vector. If that were, I'm not saying that is, if that were a vector, then then this operator is just simply let's say it's an L. Okay, so that is saying that my L brings u to 0. So if I regard u as a vector and I regard my L as a matrix, then by the definition in the linear algebra, and I can say that u should belongs to the kernel of L. Right? U should belongs to the kernel of L. Okay? And that means that as long as I can define the kernel L, then actually I have found a space that represents all the solutions, right? Because again, what does it mean by a solution to this PDE? The solution to this PDE, the U should exactly satisfy that this operator, okay, this linear operator or differential operator, the action on U that will be sent to 0. Okay, so any U that satisfies that it is inside the kernel of L should exactly be the solution, okay, to this particular function. Okay, so or let me if I would like to write it down in a more straightforward way, then I'm going to say that U belongs to the kernel of L is equivalent to that U is the solution. Okay, U is a solution. Then the problem becomes, our issue becomes, how can I explore the structure of the kernel there? How can I explore the structure of the kernel there? Okay, so that if you wanted to do that, because you see this is so far a second order. This is a second order differential operator, which is not that straightforward to understand. Therefore, what we have chosen to do was to utilize the knowledge that we have learned the last time, which is the factorization of operators. Right? Factorization of operators. What we can do is that, well, this is somehow if I'm having something like t plus cx, sorry, t squared minus cx squared, c squared x squared, okay, equals to 0. If I'm having something like this, okay, and if I would like to do the factorization, then it's actually something like t plus cx, and then t minus cx, right? Then actually, with the same logic, with exactly the same logic, I am able to factorize the second order differential operator into the product. Okay, I'm going to let's say quotation mark. This is the product. And I'm going to explain why I'm using the quotation mark later. Okay, so it is the product between two first order differential operators, which is partial t plus c partial x, and then partial t minus c partial x action upon u equals to 0. Okay, and when I'm saying the product, when I'm saying that why we should add a quotation mark on this product, this is because the product is on the sense of what? It is on the sense of operator algebra, or let's say it is on the sense of matrix multiplication. Okay, again, if you regard if you regard this second order differential operator as a L, and if you imagine that L is a matrix, then actually here I can say that this is actually my L. Let's say this is my L1 and this is my L2. Right, and this is basically saying that my L1 multiplied by L2, okay, again, assuming that these are two matrices, right, my L1 multiplied by L2 equals to L. Again, this is operator, 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 and operator. Or, if you regard it as matrix, this is actually matrix multiplied by matrix, and again, you obtain a matrix. Since this is matrix multiplication, right? Do we have computation rules for matrix multiplication? Do we have commutation rules for matrix multiplication? Do they commute? Do L1 and L2, do they naturally commute? They usually do not, right? Usually, if I'm having A as a matrix, and B also a matrix, actually A multiplied by B doesn't equal to B multiplied by A, right? Right. This is where we should exactly be careful when we are looking into the so-called the so-called factorization and multiplication, okay, for the operators. Okay, but it's just that in this case, it is commutable. Okay, in this case, it is commutable because we're having that. What we're having that is that. So in this case, we see that L1 multiplied by L2. Okay, and then let's say partial t minus c partial x and partial t plus c partial x action upon u. Okay, that will also give us that will also give us, okay, partial t minus c squared partial x u equals to 0. Okay, so in this case, okay, in this case, we can say that, okay, L1 multiplied by L2 equals to L2 multiplied by L1. Okay, they do equals to each other. It's just that in this case it is commutable. In this case it is commutable. Okay, and you might be, the next interesting question will be, okay, when would the multiplications of operators are commutable? When are they not commutable? Okay, and what I can tell you is that, well, okay, so if there are no functional coefficients, okay, if there are no functional coefficients, then they are usually commutable. If there are functional coefficients, okay, they are usually not commutable. And let me explain what does that mean. Okay, so imagine that you're looking into, so something like, let's say, okay, so imagine that, okay, so let's just say I'm having my, I'm not diving too deep, okay, into this topic, okay, but let's just give an example. Let's say I'm having partial x, I'm having another partial x, okay. Of course they're commutable, right? Or let's say, yeah, okay, of course, let's say partial x, let's say partial t, okay. Of course they're commutable. We are always assuming that my partial x partial t equals to partial t partial x. They're commutable. That's true, okay. But if I am adding another thing to this partial t, let's say I'm adding an ax, okay? Imagine that I am adding an ax to the partial t. Then, if we do want to commute, okay, if we do want to commute, that means that we'll be having something like ax, okay, partial t, and then action upon partial x. These two things are no more commutable anymore. So that's good because of what? Because you see, when I'm doing a partial x to ax dt, actually I also need to have I'm also going to produce a term that's something like a prime x multiplied by partial x partial t, right? And that is actually not included on the right hand side, right? So generally, if we are having, so here we see the coefficients. What are coefficients to these differential terms? This is 1 is constant, c is constant, 1 is constant, c is constant. Okay, so they are commutable. In that case, they are commutable. Okay, if unfortunately they have functional, okay, as their coefficients, they're usually not commutable, and you need to check. You always need to, again, so the take-home message is that when we are talking about the factorization, okay, and the factorization and the multiplication of differential operators, okay, we should be very careful about that. We should be very careful about that. And we should exactly regard them as the matrix. Since matrices are not naturally commutable, the operators are usually not naturally commutable. Okay, so that's exactly what I would like to put over here. So the next thing is that now you see, here it is about, then this has been okay. Then this is the whole equation over here, because we were looking into the solutions for L u equals to 0, right? And now it is written as L1 multiplied by L2 equals L1 multiplied by L2 u equals to 0, or because it is commutable, I can also write it down as L2 multiplied by L1 u equals to 0, right? Since L1, L2, L, all of them are linear, right? All of them are linear. Therefore, if my u are really happens to satisfy that, for example, if my L2 u equals to 0, or if my L1 u equals to 0, and actually I'm done, right? Because if L2 can already send the u to 0, then L1 action upon 0, linear, it is 0, right? Same logic, if my L1 can send the u to 0, then L2 action upon 0 is going to be 0. Okay? So therefore, we can say that if my u satisfy that, okay, if my u satisfy that is in the kernel of L2, or if that can satisfy that u is in the kernel, okay, of L1, then both of them can give us the solution, which is that in that then my u belongs to the kernel L. Okay, so then what we can do is that, okay, so now let's just try to dive in. Okay, what is exactly the kernel of L2? What is exactly the kernel of L1? the kernel of L2, which means that if I want my L2u equals to 0, then you see by my definition, that means that my partial t minus, partial tu minus c partial x u equals to 0, or, okay, so probably this is not the best way to write it, but let me say that this is actually ut minus cux equals to 0, right? And my L1u equals to 0, and that will give us ut plus u plus cux equals to 0. Okay, these two are exactly first order linear partial differential equations that we have talked about. Okay, and these two things will exactly, give us, this will give us the solution. Things like u equals to f x plus ct, right? This will give us something like u exactly equals to g x minus ct. Okay, so good. So good. This is by I'm not just trying not to spend the time on how to solve these two first order linear equations, because you should have a very good grasp of them. Okay. Then you see, again, it's linear, right? It's linear. So you see, if my u1 happens to be the solution, like in this one, right? So my u1 now, you see my u1 is a solution, and my u2 is also a solution, right? What can I say about their sum? The sum is also a solution. Again, that's because that is because the operator L is linear. Right? The operator L is linear. If I'm having LU1 equals to 0 and LU2 equals to 0, and then of course that can give us that LU1 plus LU1 plus U2. Okay, this guy is also 0. Right? Then I can say that xt, which is the sum of U1 plus U2, fx plus ct, and then plus gx minus ct. Okay, this of course is again a solution. This is a solution. Okay, this is a solution. Are we done yet? Are we done yet? What else do we need to do? Sorry? We need to yes. So and also need to we also need to rule out all other possibilities. Right. We also need to say that, okay, so indeed this is a form. This is a form of the solution. This is a form of the solution. And we also need to say that, okay, they are indeed the form of every solution. There are no others, there are no other form of solutions. Okay, we also need to say that. How do we do that? Well, then it seems that the method derived from the linear algebra is simply, it seems to be stopping here. Right, because you see, this is the form of solution that we have guessed, that we have derived by restricting our choices, right? Because you see, this is derived by what? This is derived that, okay, so instead of looking for the solution for LU equals to 0, we are actually turned to seek the solution that satisfies that L2 equals to 0 or L1 equals to 0. That is actually a restriction. Right? Because originally our target was to solve a broader question. Instead, we turn to solve two more narrow questions. Right? Okay. And so this is what we have guessed by deriving, by putting all of the results of the two restricted questions together. Okay. So what we now need to do is that we need to rule out that, okay, or we need to rule out all other possibilities. We need to prove that these two, okay, so any solutions, okay, so what I should say is that any possible solution should be exactly this one. Okay, any kind of solution should be exactly this one. And what can we do to derive that? Well, okay, this actually we can do that in multiple ways. And let me try to first talk about the so method 1. Well, this kind of method, okay, this by the factorization, okay. Let me call this to be my method 0. Okay, the method 0, it doesn't solve the questions in a completely in a completely clean way, but it's on a higher level, okay, of viewpoint. Okay, this is exactly why I would like to introduce it before we introduce the two other methods, okay, to write out the book. Okay, because if you want one day, if you want to get into the operator algebra, okay, or in the further studies of partial differential equation, then you will be recalling this lecture, and you know that, okay, now at some point I have heard that, okay, what I can do about the operator, about the differential operators. Okay, but let's come back to, if we come back to the book. Okay, so let's say method number 1. This is actually the second method in the book, but let's say this is the method number 1, and we are going to say that, well, this is actually the characteristic coordinate. Characteristic coordinate. Okay, and you might be interested in, well, what is the characteristic coordinate? Does that have to have anything to do with the characteristic lines? Well, the answer is that it has everything to do with the characteristic lines. Okay, characteristic coordinates are exactly produced, okay, by the intersections of two groups, two different categories of characteristic lines. Okay, so again, this is done by changing coordinates. Okay, this is done by changing coordinates. You see, originally we have already got the partial, the UTT. Sorry, let me still write in the operator form. UTT partial TT minus C squared partial XX U equals to 0. Okay, and we have already written it down as partial T minus C partial X partial T plus C partial X U equals to 0. Right? We were trying to look for, okay, the answer for this. Now you see, since I have already written that into the multiplication of two first-order differential operator, okay, and using our old wisdom, you see, what we can do is that this actually indicates what? This actually indicates a directional partial derivative. This is another directional partial derivative, right? As long as I can change the ordinate to legitimately, okay, rewrite these two things, okay, into the two different directional partial derivatives, then I'm possibly done. So you see, my motivation is that I would like to find the two coordinates. Okay, I would like to find two coordinates. Sorry, actually that's one coordinate. I will find a new coordinate. Okay, a new coordinate. Let's say Casi and eta. Okay, Casi and eta, such that my partial Casi exactly equals to partial t minus c partial x, and my partial eta exactly equals to partial t plus c partial x. Right? If I could do that, I'm not saying that I can absolutely do that, but if I could do that, if I could do that, then this equation can be rewritten into partial Casi, partial eta, u equals to 0. Then I'm literally done. Right? Because the solution will be what? The solution will be either partial eta, okay, partial eta u equals to 0, which means that u should be exactly a function of Casi, okay, or partial Casi u equals to 0. That will give us that u exactly should be a function of eta. If I could change the coordinate, okay, and derive such a eta and Casi. So let me, okay. If I can find the new coordinate eta and c, such that the partial derivatives on the two new directions could satisfy this. Okay, could satisfy, exactly satisfy this. Then I will be able to rewrite the old partial differential equation into the new partial differential equation, which is exactly partial c partial eta equals to 0. So far so good. So far so good. Okay. If I have that, then the solution can be come up with direct integration. Okay. Then the solution can come up with the direct integration. Okay. And the question, of course, this will give us that u equals to f plus c plus g eta. Okay, then again the question is that how do I find such c and eta? Because I don't know what is c, what is eta yet. I need to write it. And I might not be able to do that. Okay. None of these are valid. I mean this is a very good trade, but none of these are valid before we can really find what is c and what is eta. Right, so that's good. So now the question becomes, okay, look for such a new coordinate. What c and what eta can satisfy that? Right? What c and what eta can satisfy that? Okay, and our suggestion is the following. Our suggestion is that, okay, let's just say that my c, okay, is a linear combination. Because you see, everything is linear over here, right? Everything is linear over here. There's no non-linear components so far. So let's just say my c is something multiplied by x and plus something multiplied by t. I don't know what is something yet. Okay, I don't know what is something yet. And my eta also equals to something multiplied by x plus something multiplied by t. Again, I don't know what is something yet. I'm assuming that eta and c, they are just simply linear combinations x and t. Okay, this is an assumption, and I don't know that is true. But if this method could work out, I'm done, right? Okay, so now let just me say that, okay, this is actually my A11, okay, and then A12, and then A13, and A14. Oh, sorry, too bad. Okay, this is actually A22, and there's no reason for me to write A13 and A14, right? A21 and A22. Okay. Or if I want to write it, in a matrix form, that's basically eta, c and eta. Okay, these two things exactly equals to A11, A12, A21, A22 multiplied by x and t. Okay, this is the matrix form. Okay, so you see now the question is that how can I determine such A11, A12, A21, A22? So far so good? So good? Okay. Now you see the question is that I would like to do this. Okay, I would like to do this by the chain rule. Okay, now I would like to do this by the chain rule. Okay. What can I do by the chain rule is that you see, okay, so now what we're going to do is that you see, okay, so originally I was having a function, uxt. Okay, uxt. Originally I was having a function of uxt. Okay, and you know, actually I find that this is probably not the most convenient way to do that. Let me try to write it down in another way. Let me try to say that, okay, so let's say my x, let's say my x equals to b11, okay, b11 eta plus, okay, b12, b11 plus c plus b12 eta, and my y, this should be t. This should be x, and t equals to, let's say, b21 eta and plus b21 plus c plus b22 eta. Okay, and you're going to find what is the reason. Because now you see, so this basically tells you, okay, that A11, A12, A21, A22 multiplied by B11, B12, B21, B22, this should be exactly what? One is changing the coordinate from xt to c eta. Another one is changing the coordinate from c eta back to xt. So the multiplication of these two matrices should be what? Exact identity, right? Exact should be identity, right? Should be 1, 0, 0, 1. Okay, and you are going to find, you are going to see why I prefer the second way, not the first way. Sorry. Okay, let's proceed with this. Okay, let's proceed with this. Now uxt equals to what? I don't want to deal with the x and t coordinate anymore. What can I say about what can I do to replace the ux and t by the Cosine eta? It actually equals to what? U what? What is x? What is x in the representation of Cosine eta? It's this, right? And this is my t, right? Okay. So this, so my uxt is exactly u, okay, b11 Cosine plus b12 eta. This was my x. This was my x. Now in the sense of Cosine eta. And what is my t? b21 Cosine plus b22 eta. This was my t. Again now Cosine eta. So far so good. Okay. See, you see, what did I want to do? I want my Cosine eta exactly satisfying these two things, right? Okay, so the question is that now what is my u Cosine, or equals to partial Cosine u? How do I obtain my u Cosine? How do I obtain my u Cosine? Come on, how do you compute the partial derivative of partial u partial Cosine? Based on the expression, based on the new expression of u as a function of Cosine eta. It should be a partial u, and this entry was x, right? So partial u, partial x, and then multiply by what? Multiply by u11, right? Because and then I need a partial x, partial Cosine. Okay, this is the first thing. And then what? By the chain rule, the second one will be partial u, partial what? Partial t. This entry was t. And then partial t, partial Cosine is going to be e21, right? Okay, or if I would like to write it down, then actually this should exactly, okay, according to the chain rule, okay, according to the chain rule, this is exactly, first of all, this is exactly partial u, partial x, okay, and then multiplied by partial x, partial Cosine, right? And then plus partial u, partial t, and then multiplied by partial t, partial Cosine. This is the chain rule, right? This is the chain rule of partial derivatives, right? It's just that, you see, my partial x, partial Cosine is exactly what? My b11. And my partial t, partial Cosine is exactly what? Exactly b21, right? So this exactly, finally, this exactly equals to, okay, b11, okay, partial u, partial x, and then plus b12, partial u, partial t. So far, so good. So far, so good. Oh, yes, b21, you're right, you're right. B2. So far, so good. Any questions so far? No? Okay. And what can I say about partial eta? Which is u eta, which is partial eta u. Again, by the chain rule, now you tell me what should be that? What should that be? Partial u, partial eta. What should that be? First of all, partial u, partial x multiplied by partial x, partial eta, and then partial u, partial t, and then multiplied by partial t, partial eta. Right? And I know exactly what is partial x, partial eta, right? It's my, let me use this color. It's my b12, and partial t, partial eta is my b22, right? So this equals to b12, sorry. b12, okay, partial u, partial x, plus b22, partial u, partial t. Don't forget what was our requirement. Let me put these two things in this on the same slide. Don't forget what was our requirement for partial Cosine and partial eta. I want my partial C exactly equals to partial T minus partial C partial X, C partial X. And I want my partial eta exactly equals to partial T plus C partial X. Now I just need to assign these values to my B11, B21, B12, B22. Yeah, indeed. You see, again, I want my U cos C equals to UT minus CUX. So this B1 should be what? Negative CUX. This my B11 exactly should be negative C, right? And my B21 should be exactly B1. Same reason, my B12 should be exactly be C, and my B22 should exactly be the 1. So that's okay. Okay. So that's basically speaking that wait a minute. So function T eta partial S. So that's basically speaking that okay. As long as I let my x okay equals to so let me try to b11 partial u partial x. Okay, so as long as I let my b11 equals to negative c, my b12 equals to b11 b12. Okay, my b12 equals to positive c. And my B21 equals to 1, my B22 also equals to 1, and actually I'm done. Or to make it a little bit more explicit, then let's say my x equals to negative c, okay, negative c eta plus negative c plus eta, and my t equals to c plus eta, then actually, okay, I'm done with that. Okay? And again, don't forget that if that can be done, then actually I am able to directly write everything like this, like this here. Okay. So let me see, it should be my C. Oh, and but however, you see, we need to write down. We need to exactly write down eta and cos C as the function of x and t, because you see, my final answer is f cos C and g eta, right? We again need to write down cos C and eta, okay, into the function of x and t. Okay, so I already know that x and t can be expressed as cos C and eta over here, right? How can I rewrite the C and eta back into x and t? How do we do that? Because C should be exactly the what? Wait a minute. Wait, is there? I might have done something wrong over here, have I? Let's see, this is not, because the final answer is not exactly what I've been expected. So let me try to see where I have done wrong.
It's correct.
Sorry?
C is like t minus x over 2c.
Sorry, which place?
That's I think it's correct.
Sorry?
I think it's correct.
You say that's correct or what?
Correct.
No, sorry. There must be something wrong because the final answer is not something.
Because when I just use A1 or A1 to solve that, and I think I get the same answer without.
Yeah. But the question now is what I'm missing. I'm missing the coefficients over here. I'm missing the coefficients over here, and okay. Give me 1 minute to check this out. okay, on the book it tells me that, I mean, I'm using a coefficients of 2c, but that should not be the problem, right? That should not be exactly the problem.
不是，等一下。
B11, B12,
因为它在两个 kernel 的 union，它是
B21, B22.
可以啊，不是，你说另外一个当时有关的，等一下，你说不是？
B21, okay, B21 equals to 1 and
不是，它只有在本地里头没有。
I see. There is a difference.
equals to 1.
不是。
Oh, sorry, it's in the last step. It's in the last step. Sorry. Okay, all of the derivation are correct, but I got a mistake in the last step. Okay, because I mixed up. Sorry, I mixed up the B12 and B21. So that's the problem. That is the problem. So okay, so you see here, as we have derived, right? You see my B11 should be negative C, and my B12 should be my B11 should be negative C, and my B12 should be C. So here is actually x equals to negative C plus C eta. That's it. Okay, that's the only thing that was doing wrong. And then B21 and B22, they are both 1. So that's it. Okay, case closed. Case closed. Okay, good. Okay, final. I didn't make a very large mistake. So it's a tiny mistake. So eta. Okay, we need to solve the eta and the C. Okay, and put them in the expression of x and t. So you see, eta can be obtained by cos can be obtained by let's see t minus cx. Sorry, it should be ct minus x. Should be ct minus x, because I would like to cancel eta, right? I would like to cancel eta, and then over to c, right? And eta could be obtained by ct plus x over 2c. That's it. Okay, that's it. So finally, what we have over here is that it gives us this, because you see, don't forget, my u, xt, okay, it was written, so the solution was something like f cos c plus g eta. So that should equal to something like f, okay, ct minus x over 2c, okay, and then plus g ct plus x over 2c. And you might be a little bit confused, right? Now you see this is my new f and g, but don't forget, my old f and g was this, right? My old f and g was this, but they are basically the same, just need to. Okay, so you see f, okay, f x minus ct, x minus ct, or g x plus ct. You just need to do some functional operations to the different f, okay, to the two f's to bring them identical. Okay, so that's good. Okay, so and again, we can just say that my u, x, and t equals to this plus this. This basically tells me, okay, that this is okay, this is the answer. Okay, and you see, and let's try to revisit. Let's try to revisit our method 1. So what did we exactly do? You see, the title for method 1 is the characteristic coordinate. And what we exactly was doing was changing the coordinate. We changed the coordinate x and t to the new coordinate c and eta, such that we could obtain the convenience, okay, in directly writing the two first-order differential operators as exactly as the partial c and partial eta. This was our motivation, right? But what did we exactly obtain? What we have exactly done was that, now you see, originally I was on the coordinate x and t, okay? Now I am on the new coordinate cos c and eta. If my x and t was something like this is my x,
this is my t, right? This is my x, and this is my t. You see, my cos c and eta, this is actually what? My cos c, okay, my cos c is actually, don't forget, my cos c is actually ct minus x, okay, over 2c. My eta is actually ct plus x over 2c, right? So if this is my c, and if this is my t and this is my x, and I know that the new coordinates should satisfy, cos c and eta should be satisfied, that these two formulas, how do I draw the new coordinate? How do I draw the new coordinate? For example, what type of points would satisfy cos c equals to 0? What type of points on this on the xt coordinates would satisfy cos c equals to 0? X should equals to ct, right? X should equals to ct. So basically, I am actually going to draw lines like this. Well, okay, so sorry, this should go to 0, right? What about the other one? What about eta equals to 0? X should equals to negative ct, right? Okay. Actually equals to negative ct. What is the slope over here? What's the slope over here? It's 1 over c. This is 1 over c, and this is negative 1 over c. Right? Okay. And similarly, if I need my cos c equals to 1 or cos c equals to 2, cos c equals to 3, then actually I'm going to have lines like this, right? Because this is going to be the constant value for cos c, constant value for cos c, constant value for cos c. Okay. This. And let me use another color. This is going to be a constant value for eta. So good? You see, these two things, these are exactly two different groups of characteristic lines. These are exactly two different groups of characteristic lines. So good? And let's see what would happen. Okay, let's see what would happen if we only had one branch instead of two branches. What would happen if I had only one branch? Let's say if I only had f equals to x minus ct. What kind of solution would that be? If I only have uxt equals to f x minus ct, let me just assume that g is a 0 function. G is 0. Okay? What would happen to my solution? Then which category of characteristic lines that we already have? Red or blue? Well, we only have red, right? I'm having f minus ct. That means what? That means that, okay, so first of all, on these lines, my solution are going to be what? My solution are going to be what? Are constants. Remember, what does the characteristic line mean? Characteristic line means that on the characteristic lines, okay, the solutions are constants. Right? The solution are going to be constants. So go up. These things are constants. And the solution solution u equals to fx minus ct. What kind of partial differential equation would give us that kind of solution? What kind of PDE would give us that kind of solution? First order transport equation. The transport equation. And what does the transport equation tell us? I mean, what kind of physical process is the transport equation telling? Just something constantly moving, just constantly moving rightwards with a constant speed, right? So that means what? That means that so these don't forget that these characteristic lines are describing something is constantly going rightwards. That's it. Something is constantly going rightwards. And now let's say I don't have the branch of f. I'm only having my g. Okay, which means that my ux equals to g x plus c with no f. Then what kind of conclusions can we draw following what we have discussed? First of all, what type of which category of the characteristic lines will stay? The blue ones, these will stay, right? And what kind of physical process is this? That's something that's constantly going backwards. Okay? That's something that's constantly going backwards. Okay, with this VC. Okay, now let's say I'm having both. I'm having both. What does that mean? UXT means that my fx minus ct. Okay, one branch is fx minus ct. Another branch is gx plus ct. What does it mean? Two branches. There are two. So these two processes, one go constantly going backwards with the wave speed c. Another constantly going leftwards with the wave speed negative c. These two processes, they coexist. These two processes, they coexist. So that's the physical interpretation. That is the physical interpretation of the wave equation. Okay, there's always a wavelet constantly going backwards and a wavelet constantly going leftwards. Okay, but how do we determine the exact f and the exact g? Okay, in specific questions. Okay, so now let's look into an example of the initial value problem. Let's say, okay, so that's actually, you know what? That's actually example 0. Let's say, because this is okay, that's actually example 0. Example 0. Okay, so again, utt equals to c squared uxx, and this is defined on negative infinity and to positive infinity. Okay, now let's say I am specifying the initial conditions. I am specifying the initial conditions. I see the initial conditions, which is exactly so. First of all, okay, how many initial conditions should I have to completely determine a solution for wave equation? 1, 2, 3. Which one? I exactly have 2, right? Because of what? Because on time, this is a second order, okay? This is the second order differential equation on time. So, first of all, let's say ux0. Okay, so this is the initial condition for u itself. Let's assume this is something like phi x. What else should I specify? Except for the, besides the initial condition for u, what else should I satisfy? I should also satisfy an initial condition for ut, right? I should also specify that ut x0, okay, is another function. Let's see, psi, not phi, but psi x. Okay, they are just arbitrary. Okay, my phi and my psi they're actually arbitrary. And you may ask, so are there any constraints, okay, on phi and psi? We're going to see. We're going to see what kind of constraints that we're going to add. Okay, so you see, first of all, don't forget my u x t. So t x u x t. They're basically the same, right? Let's say u x t. Okay, let's say my u x t. Okay, this equals to. Don't forget, this equals to f. Okay, f. Okay, f x. What do I use? Okay, so x minus ct, and then plus g x plus ct. Right. Well, you see, by setting t equals to 0, what can I have? Because you see, this is the initial condition. This is the initial condition. This is the solution that I have obtained. What I need to do is that I would like to determine what's f and what's g. Right? So now you see, by setting t equals to 0, my u should exactly satisfy my initial condition. Right? So that basically tells me that by setting everything to 0, then actually u x 0. This is actually what? By setting t equals to 0, that's actually fx. By setting t equals to 0, that's actually gx. And I know that this is actually phi x. Right? This is given by my initial condition. So that's good. And also, how can I utilize the psi? How can I utilize? So I have just, you see, I have two initial conditions, and I have just used up one of it. How can I utilize the second initial condition? Differentiate what? Differentiate my uxt at which place? At t equals to 0, because this is the part of the root ut. Okay, exactly evaluate at 0, right? Okay. So what we're going to do is that. So ut x 0. We know that it's actually psi x. Okay. This is exactly partial u x t, partial t, and evaluate it at t equals to 0. Let me be a little bit more rigorous, right? So this is exactly partial f x minus ct. Oh, sorry about that. And then plus g x plus ct, partial t, and then evaluate it at t equals to 0. How do I proceed? What is partial f partial t? What is partial f partial t? Sorry, what is how do I compute? How do I compute this partial derivative? How do I compute this partial derivative? Chain rule, right? Chain rule. So first of all, by doing the first order derivative, I need to obtain an f prime. That's going to be f prime, right? And whatever is inside the bracket, that's a function of both c and t. So by the chain rule, I need to obtain a negative c. And so the first term is going to give me a negative c f prime, and then x minus ct, right? And then the second one is going to give me what? C g prime x plus c. This is again evaluated at t equals to 0. So if this is evaluated at t equals to 0, that means that my t equals to 0 and my t equals to 0. So what I'm going to have is exactly, negative c f prime x, and then plus c g prime x. So far so good. So good. So to summarize a little bit. That give us two things. The first initial condition, which is u x 0 equals to phi x. This has already given us one relation between f and g and phi, which is fx plus gx, equals to phi x. And the second initial condition, which is ut x 0 equals to psi x. This gives us another initial condition. Let me just simply try to let's say we divide c on both sides of this equation. Let's say we divide c on both sides, then what we're obtaining is negative f prime x, and then plus g prime x equals to psi x over c. To summarize, these are the two new relations that we have obtained. That my f and g should be exactly satisfied. So what's good? Well, how do I proceed? Well, you see, the first one is about f and g, right? It tells me that f, the left hand side equals to the right hand side. And the second one is about the first order derivative of f and g. They are not on the same order. They are not on the same level. So what I prefer to do is that I can differentiate. I can differentiate the first equation towards x on both sides. Then I'm going to obtain f prime and g prime and the left hand side as well. So the first equation, if I continue to, let's say, we take the derivative, let's say we take the derivative, then what we're having is f prime x plus g prime x equals to phi prime x. Right, my f prime x plus g prime x equals to phi prime x. Well, you see, combined with the second one. The second one is about negative f prime x plus g prime x equals to phi equals to psi x over c. Right. So finally, okay, we can obtain the exact expression. We can obtain the exact expression of f prime and g prime, not f and g, but f prime and g prime, which is exactly f prime equals to 1/2 phi prime minus psi over c, and my g prime exactly equals to 1/2 phi prime plus psi over c. This is just okay. I have, of course, I have jumped one step, but you see, this can be just done by, for example, if I want to obtain g prime, I just need to add this equation and this equation up, right? If I want to obtain f prime, I just need to use the first equation minus the second equation. Right, that's very straightforward. Okay. So if this is my f, how to obtain? So if this is my f prime, how do I obtain my f? If this is my f, how do I obtain my f? I can just directly do integration, right? Because it was differentiation. Now, by doing the integration, now what I am having is exactly f x, equals to 1/2, because I'm doing the integration. So the first term will be integrated, and then plus 1/2c, sorry, actually minus 1/2c. Let's say I'm integrating exactly from 0, and then towards x, and then the psi, and let's say this I'm integrating upon x prime, dx prime. Of course, because I'm doing the integration, so that's me plus the constant term, which is a. So far so good. Okay, what about the other one? What about the other one?
Just plus.
Okay, again, same thing, right? Gx should be what? 1/2 phi x, and then what? Just changing everything from minus to plus, right? Plus 1/2c, from 0 to x. From 2c from 0 to x, psi x prime dx prime, and then plus b. So good? So good?
Can you explain why it's x prime instead?
Sorry?
Why is it x prime?
Oh, I'm just okay. So if you are happy with the x prime, right? Of course. So I'm just saying that it's a variable that I'm only using for integration. If you are unsatisfied with the x, I can change it up to, for example, to y. I can use another variable. Let's say y dy. I'm just saying that. Let's say that's a variable. What I'm doing is that what I'm trying to do. So integrate from y to x. Okay. Well, one last step. Don't forget, my u xt equals to what? My u xt equals to f x minus ct, and then plus g x plus ct. Right, so I need to put these two things back into the expression of the solution. Right? Okay, so I'm going to do that for you. So which is exactly 1/2 phi x plus ct, and then plus 1/2 phi. Oh, sorry. Yes, phi x minus ct. Okay. X minus ct, and then plus 1/2c. Integration from 0 to x plus ct phi. sorry, psi, okay? Let's say y dy, and then minus 1/2c from 0 to x minus ct, okay? Let's say psi y dy. The first two things are actually not so algorithm, right? The first two things. The first two things are not so algorithm. So let's just say this is actually 1/2, okay, phi x plus ct, and then plus phi x minus ct. Let me use a square bracket for that. Well, the second parts are the two integrations. Oh, and you may ask for what about a and b? Well, it doesn't matter, because whatever a and b is, they should exactly cancel each other. Right? They should exactly cancel each other. Well, otherwise, how do you obtain? Okay. Otherwise, how do you obtain f plus g equals to 5? Right. How do you obtain f plus g equals to 5? Okay. So you see, the question is about how can I simplify? Can I further simplify this guy? Can I further simplify this guy? You see, the first one, first of all, what are the common points? They both have a coefficient of 1/2c. 1/2c. This is integration of phi from 0 to x plus ct. Okay, so which means that from 0 to x plus ct. This one is again an integration from 0 to x minus ct. Right, but don't forget there's a minus sign. There's a minus sign. So that's actually the integration, the larger part of integration, but getting rid of the shorter part, okay, which will be exactly the integration of the remaining part, which means that I just need to add one more thing, that is 1/2c, and then the integration from x minus ct to x plus ct, and then psi y d. That's it. That's the whole expression. That is the whole expression for uxt as the solution to the wave equation. Okay. Let's take a 5 minutes break.
是因为过敏地啊什么的，滴完它反而会痒。
是滴了就不会痒了。
但是如果怕你滴完还在挠，
不是，主要是有部分痕迹太少，没有覆盖到整个眼球。啊，它这个有点吓人，你知道吗？
怎么了这里？
它就是按压下去，然后这样子的，然后给人一种非常……
那你那样它会把这个东西按到。
不是，主要是我对于这个东西的恐惧。
啊，我知道，就是它本来那个头它不会动，但是你按压就会感觉它可能会冒出来。
是的。
啊，我懂了。你需要一个把掐，就是一掐才会滴出来那个东西。
是的，我觉得普通的那种滴瓶就挺好，为什么一定要换呢？
你原来是按压式的，天啊，真的很吓人，我觉得。就你潜意识里会总觉得它会把这个头按出来。
对的，这是不合人的那种潜意识。啊，天哪！可以。有狗人士就是好。
有什么？
有狗人士。
他这耳朵是练起来的，你知道吗？他一睡觉耳朵就
啊，它平时是塌的吗？
平时塌下来的，平时站起来的塌下来的，然后他
睡觉反而会立起来。
睡觉就是
重力问题。
闭着眼睛假睡的时候，或者是闭眼就趴着的时候，那耳朵是塌下来的。如果他真的要睡觉，睡得很沉的时候，耳朵是竖起来的。
好神奇。
是这样的。
好神奇。
特别喜欢看他耳朵竖起来的，像一只小狼，真的。是啊，耳朵下垂下那种狗。
那为什么不养那种很像狼的那种狗呢？
是有这种抓到了谁就养什么。我们带着蛋黄去看他的妈妈和他的兄弟姐妹，但是走到这边，原来那个看着不是他们家那个狗窝是空的，狗盆都没有，说明这个狗已经很不在了，不知道小狗可能就一直送出去了，送出去了，那狗妈妈是不是卖给狗贩子不想去想？
真的老死了呀！
不是啊，这怎么可能是刚生下来的？
有没有可能就是因为生小狗，然后导致身体状况下降特别快，然后就急了。
一只狗它一辈子要生很多狗，
但是养疯狗儿了。我们学校就是我们学校以前就是校园猫，然后就是它在临终之前下了一窝崽，然后就第二年就挂了。
哦，那3只小猫的妈妈估计是这个情况，因为我们至今没有看到它的妈妈。但是我们家里爆蛋黄的时候，那时候这狗妈妈是带而不是死掉，是正好出门了。然后我家就不愿意想了，但是真的给狗饭。
以前这狗卖不了多少钱，养在那儿看家护院，然后一天也不用费多少钱去养它。
那个地方不太需要看家护院，连地都没有，和一个农家大家都一样，那需要什么看家护院？不需要。
但是我觉得农家才更需要看家护院，因为
那是城乡结合处，它不是种地，它就是大家
之前江西不就是那种就是流动人员，我比较
就那个地方是大家会彼此都认识，然后都是都会搭起亲缘关系，然后彼此认识。那个地方确实很破败，垃圾的狗，他们家养狗都不喂，完全是在垃圾堆里找吃的，看看。
哦，那有可能那狗其实完全是逃了而已。
狗不喜欢家里，它不会跑。
真的吗？
而不喜欢走狗不是家里。
但是 是这只是俚语，然后我想知道它到底就是它仅仅是这么说，就是做一个比喻，还是狗真的不会跑？
如果他真的把这个人当成了主人，一般对家里的小孩子跟着狗非常亲，然后大人家看着狗老是挨狗带着小孩就拼命踢着狗，快跑快跑，踢它一脚它还跑不了，后来真的被卖出去收掉。
哇，真的吗？
看过很多就是小孩看到一些成年人喜欢演的，那是看那种体育这样，拼命踢狗，然后踢的很踢的一脚狗还是做不了，真的是小孩脚抬后来就被抓住了。反正就是这样。
狗贩子买狗干什么呢？狗贩子买狗拿去干什么呢？
狗肉，吃肉，
这样不健康吧？就是不是说现在狗肉都是那种就是狗肉厂里面养出来的狗，然后那样才可以通过食品标准，然后剩下的就是宠物狗之类的不太干净。
就是食品安全一直都是问题，
就是说，因为狗肉本来就有一点那种非法的性质在里面，是吧？
就是可能是一盘猪肉感觉气质是不错，下三万。待会儿猪上养的都吃肉，甚至还有人去人家猪人家宠物小疗伤卖肉，或者是渠道，你没听过吗？
Okay, so let's continue.
那种极少数发生的那种很恶心的事情。
Okay, so again, this is the derivation of the general solution. Or actually, the general solution to the restricted by the initial conditions. That if I set the original u, the initial conditions for u at 0 equals to phi, and the ut equals to ut at 0 equals to psi. Well, don't forget this is the wave equation. This is the wave equation, and this is the actually describing the possible movements of completely vertical movements for a string. So can you please tell me what is the physical interpretation for u at x0 evaluated at x0 and ut evaluated at x0? What are the physical interpretations for them? Or in other words, what I am exactly fixing by posing these two initial conditions? This is the initial position at x. This is what? Initial what? Initial velocity or initial speed. Well, both are okay, right? This is the initial velocity. Well, if you count the directions of the movements, that is the initial velocity. Right? This is the initial velocity at 0. So you see, what are we exactly posing at the very beginning is exactly the initial position and the initial speed. Don't forget that when you folks were learning ODE, okay, especially for something that's respecting Newton's law. So for example, when we are having something like m x, okay, x prime prime, and then let's say plus let's say k x prime, and then plus a h x equals to something like f, okay, this kind of things. Oh, sorry, there's no dots. Okay. This is actually a vibration for single point, right? For that, we also needed to do what? We also needed to justify. Okay, we also needed to justify what is x0 and what is x prime here. Right. This was exactly the initial position and the initial speed. Right, the initial position and the initial speed. We're doing exactly the same thing over here for the partial differential equations, but it's just that now I'm not only specifying the initial condition for one point, I'm specifying the initial condition for every point on the string, and systematically, okay, by the phi x, psi x, okay, initial position and initial speed. Well, okay, what does this tell you? So basically, so this basically tells you this. So this is the expression for uxt.
How many components are there in the solution? There are 3, right? Well, actually 2. U, X, T, is the sum. So you see, it relies on, first of all, you see, it indeed relies on both of the initial conditions that I posed. It indeed relies on the initial positions, and it also relies on the initial speed, right? As for the initial position, it actually only relies on the 2 points of the position, right? It only relies on what was the position. So for the position u x t, okay. So for the position of certain point at x, okay, and at the time t, its vertical location. First of all, its location. That is vertical location. It relies on the two vertical locations of the 2 points evaluated at x plus ct and x minus ct. And also it relies on the speed, okay, the initial speed, which we should integrate, okay, which we should integrate, okay, in the middle. So let's try to look into two different examples, okay? Then we are going to have a better understanding of what's happening here. So the first thing, so now let's say example number 1. Okay, example number 1, this is the real example number 1 in the book. Let's say phi x equals to 0. Okay, phi x equals to 0. And psi x equals to cosine x. Oh, what does that mean? Phi x equals to 0. And psi x equals to cosine x. So which means that initially all the points are at 0. All the points, so which means that initially the string was straight. But there are different speed, right? There were speeds everywhere, right? There were speeds everywhere, the cosine x. And you see, because cosine x is a periodic function going up and down, up and down, up and down. Somewhere it's positive, somewhere it's negative, which means that the initial speed, at some locations the initial speed will going upwards. At some places the initial speed will going downwards. That's where the vibration comes in, right? But what does that tells me when I'm trying to express my u xt? What does that tell me? What does that tell me when I'm trying to express my u xt? So that means that my first component is actually doing what? That's going away because there's no phi. Phi was 0. Phi was 0. Not all of it, phi was 0 everywhere. Right? I'm only having the second one. I'm only having the second one, which is 1 over 2c. Okay, integration from x minus ct to x plus ct. Okay, psi y dy. I'm only having that. So that means that the integration at certain interval, okay, the integration at certain interval of the speed, it exactly determines the location of my x at a later time. So after that, okay, so this is example number 1. And if you're interested in the solution to this equation, you can just check the example number 1, and the book tells you to verify that is indeed the solution. I'm going to jump test that. I don't have time for that. But the more interesting part is the example number 2. Okay, example number 2. Now, instead saying the initial position is constantly 0, let's say the initial speed is constantly 0. Let's say my psi x was 0. Again, there's no initial speed, okay? There's no initial speed. However, my initial, so first of all, if my initial speed, so let's look into a very specific case. If my phi x is 0 everywhere, and my psi x is also 0 everywhere, what would happen? What would happen? If everything will stay 0 and 0 everywhere, right? Because there were no initial displacement from 0, and there were no initial speed. which means that on the string, every single point will stay exactly where they should be. Okay, so no vibration. And indeed, you can see that from the formula, uxt equals to something from phi, something from psi, but if everything is zero, then uxt is going to be zero everywhere, every time, all the time. Right? So that means that there is not going to be any movement anymore. But in this case, only the initial speed is zero. But as for the initial location, that means actually the phi x, okay, let me assign it carefully. Let's say that okay, so let me put the sine x equals to 0 a little bit further. Okay? So let's say for x, for the absolute value of x be smaller than a, my phi x is actually b minus, okay, bx over a. Absolute value of x over a. Okay, this is for x be smaller than a. For any x that has absolute value to be larger than a, I'm having my phi x equals to 0. So what does that mean? Okay, what does that mean? That means that this is exactly the initial position. Okay, phi x, I'm now going to plot phi x as a function of x. So first of all, for anything that's away, let's be larger than a or be smaller than negative a, because their absolute value is larger than a, so it's going to be 0. Okay, it's going to be 0. Okay, it's going to be 0. So that's good. And what will happen for x equals to 0? When x equals to 0, it falls in the absolute value is smaller than a. And which means that it should be exactly b, because x is 0, right? So when x equals to 0, the phi x is over here. The phi x is over here. And when this, and you see that because these are two linear functions, right? These are two linear functions. And these two linear functions are exactly, okay, these two, this is a piecewise linear function, right? This piecewise linear function is exactly connecting these 3 points. Right, so this is what it looks like originally for this string. This is what it looks like originally for this string. So that's good? Okay, so this is the initial condition. Now, can you tell me what, now you see, can you tell me what is ux? What is the solution? What is the solution? Let me put my ux over here. What is the solution? Why don't we just spend 2 to 3 minutes, okay, try to use the formula that we already obtained, okay, to write down the ux. Don't forget, my initial speed, my psi x over here, my psi x is 0, right? Which means that the integration part goes away. I don't have this integration part. I'm only having the 2 phi, x plus ct and phi x minus ct. I'm only having that, right? Can you please derive exactly this form of uxt, sorry, not ux, but uxt, the solution uxt, okay, based on the formula that we have just given. Let's spend 2 to 3 minutes to do the computation. So sorry, I have to stop you for now because we will have more time to spend on this. But you should soon realize that actually this is not that straightforward, right? Because you see, when I'm trying to, because so first of all, we don't need to care about the integration part, but still, okay, still we need to assign the values for u x t, which equals to 1/2, okay, phi x plus ct and plus phi x minus ct, right? However, the phi actually is not, it's actually a piecewise defined function. Phi x, but the initial condition was a piecewise defined function. So you see, that depends on the following. That actually depends on the order or the relationships of the following 5 numbers. First of all, you see 0. Right? 0 is the boundary points. Okay, for going up or going down. And of course, plus or minus 8. 0, 0, plus or minus 8. And then it's about where does my x plus ct and x minus ct falls in, right? If, for example, my x plus ct falls here, it's going to be 0. But if my x plus ct falls here, it's going to be some sort of positive value, right? Okay, and then x plus or minus ct, right? There are actually many different cases, okay, that we need to discuss. Okay, so it will actually take some time. To derive the whole, to derive the exact, relationship, for these guys. Okay, but what I'm going to do now is that I am going to give you exactly certain selections. Okay, I'm going to give you certain selections of the t. We are going to study uxt on several carefully selected time sections. Okay, then we are going to understand how does this equation evolves. Okay, so the time points that I'm going to give is exactly t equals to 0. So first of all, t equals to 0, and then t equals to, let's say, a over 2c, and then t equals to a over c, and then t equals to 2a over c. Let's see what we have. Okay, let's see what we have. First of all, let's say t equals to a over 2c. T equals to a over 2c. Then here, according to my expression, then actually my uxt equals to a over 2c, right? So that's actually 1 over 2 phi. Okay, first of all, 1 over 2 phi, x minus, x c, t equals to a over 2c plus a over 2, right? And then plus phi x minus a over 2. Right? X plus a over 2, and then phi x minus a over 2. Well, you see, as long as we can define, as long as we can see what is phi x plus over 2 and phi x minus a over 2, and then we take the average, we're done. Right? So question 1, what is phi x plus a over 2? We need one function that's x plus a over 2, and another function phi x minus a over 2, and then we take the average. And then we take the average, 1 over 2. What is phi x plus a over 2? This is my phi. This is my phi. So my phi x plus a over 2 should be exactly this guy moving towards which place? A is a positive number. So that is actually a translation going leftwards, right? This is going to be a translation going rightwards. So what I am having is that, first of all, okay, this guy going leftwards, and which means that this point will be located at negative 2/3/2, right? This point is going to be located at, okay, a/2. Okay, and then I am having something like this. Okay, so this is my phi x plus a/2. What about the other one? What about the other one? The other one should be exactly here and here, right? And then another triangle. This place is negative a/2, and this place is negative 3a/2. Okay, now what I need to do? Now what I need to do is taking the average. I just need to take the average. But you see, what can I say for the function values in this place? What can I say for the function values between, when I'm taking the average, I need to sum up these two triangles, right? And then divide by 2. Well, what is the sum of these two triangles between negative a/2 and a/2? It's actually a constant, right? Because one branch is going constantly up, another branch is going constantly down. It's actually a constant, right? So what I know is that actually over here, okay, is the constant. And because for the other branch, so you see for the two branches on the sides, okay, I just need to connect that with the intersecting points at 0. Right? And that's it. That's it. That's exactly this is exactly my ux, okay, a/2c. Okay, this is my ux a/2c. What about the other? What about the next one? Let me erase this. Okay, so now I'm going to study t when t equals to, let's say, a/c. So I'm going to study ux a/c. ux a/c should be exactly the average point of phi x now plus what? Plus a. Probably should close the door. Okay. And then phi x what? Minus a. Right. What is phi x plus a and phi x minus a? That should be the original triangle moving leftwards for a and then moving rightwards for a, right? Okay. So that's going to be exactly, okay, so first of all, moving leftwards for a, I'm going to get this and this. So negative 2a, 0. And here is going to be negative a. Moving rightwards, it's going to be this and this. Okay, this is going to be a. This is going to be 2a. This is going to be a. Okay, these two triangles sums up. It will be exactly the same thing, and then we take the average. So the answer would be something like this. And then going up, going down. So far so good. So far so good. What about the next one? What about t equals to 2a/c? What about t equals to 2a/c? Do you find the rules now? Do you find the rules now? Okay, so for ux 2a/c. So now it's about the average of which two functions. 1/2 is going to be about the average of what? Of phi now it should be x plus what? It was 1/2 a/2a, and now it should be what? 2a. And phi x, and then what? Minus 2a. So now it's the displacement of my original phi. Now going leftwards for what? For 2a, and going rightwards for 2a. So I don't have enough space for that for now, but what we would imagine is going to be something like See, these two small triangles, right? They will be going left and going right for more, right? So exactly what we're exactly going to have should be, okay, this guy started from -2, -a, okay, and then, so -a, -2a, and -3a. Let me use another color. Okay, and the right branch is going to be starting from a, 2a, and then 3a. And then use another color, that's going to be mine. Okay. So I'm now putting the 4 images together. What can you conclude? What do you conclude? For the results of this wave equation. Don't forget, what kind of physical process are we describing? This is the wave equation. It's just that we're having a special initial condition for the position, but the initial speed will be exactly 0. When the initial speed is exactly 0, what's happening in the solution formula is that the integration part, the integration of the initial speed, this will goes away. And what we're only having are the two leftwards, are the two drift terms. One term represents the drift towards left, and another term represents the drift towards right. Right? And you see, what's happening over here is that we can assume, we can pretend, right? You see, we can pretend that initially, you see, there are two such kind of triangle that actually where its vertex is located at b/2. We're having two because the you see the original the red triangle is actually what? It's actually the sum of the two blue triangles, right? What we can assume is that there were two blue triangles, okay, that was over here, okay, and then these two blue triangles are going out and out and out and out and out, and one branch of the blue triangle is constantly going left, and another branch of the blue triangle is constantly going right. And the results is always the sum of the two blue triangles. So far so good? You see, at this place, the wave equation is exactly equivalent to the results of two drift equations, but it's just that one is going left, another one is going right. Okay, so far so good. So this is the example of the this is the example that we should discuss for the drift equation. And we're having 15 minutes left, and probably this is good for me to illustrate my last point. Okay, this is probably good enough for me to illustrate my last point. And so let's say this is actually something about 2.2. Okay, this is something about 2.2. How large was I writing? I was writing this much. Okay. So 2.2. The first thing of the 2.2 was the causality of the wave equation. Again, let's try to revisit what is the solution looks like. It's uxt, okay, equals to 1/2 phi, okay, x plus ct, and then plus phi x minus ct, and then plus 1/2. Okay, let me write it on another line. Okay, and then sorry. And then plus 1/2c, okay, the integration from x minus ct to x plus ct phi s ds. Okay, this is the solution. The causality is the following. If, let's say, I am perturbing the initial condition for a little bit, I am perturbing the initial condition for a little bit at a certain point. Okay. When I'm going to when the time evolves, how does the perturbation evolves? What does it do to the following solutions on time? Cause and effect. The cause is that I am manipulating the initial condition in some sense. And the effect is what is my consequence? What is going to be caused, okay, in the following time? So the first thing, okay, is that, let's say, the first thing is that, now let's say, I am doing I am perturbing some certain things. Okay, let's say on x0. I am perturbing on x0. Okay. I am perturbing on x0. Well, if I'm perturbing at the x0, then let's say I'm perturbing both, let's say, phi and psi at x0. I'm perturbing that a little bit. Okay. So, what effect does it bring? What effect does it bring? You see, it only, so let's say for the phi, for the initial perturbation at position phi. First of all, it only has the it's only changing my solution uxt. Okay, whenever the x plus city or the x minus city touches my x0, right? It's only changing my mu. Okay, at this point, whenever my x plus city or x minus city, whenever my phi x0 should be referred to. Whatever my phi x0 are referred to. So don't forget. So let's say this is my x, this is my t, and here's my x0. What are the two characteristic lines that are crossing the x0 at 0? This point is x0, 0, right? What are the two characteristic lines that are crossing that point? One going right up, and another going left up, right? So this is one point. So this is one characteristic line, and this is another characteristic line. And these two characteristic lines exactly describe, okay, the trajectories that my phi x velocity and my phi x minus c. So whatever that I change on this point, at this point, okay, it's only going to change. So the change on this point, okay, are going to be here, nowhere else. When time evolves. So let's say originally, if I ignore the contribution of the initial velocity, so let's imagine here, okay. Let's going back to our example over here. This is the case that we have been ignoring the initial velocity. So imagine that I have something that I am. Let's say I am initially I am, let's say, this peak. Okay, if I am doing a small perturbation, I am decreasing the small peak to this place. Okay, I'm decreasing the small peak to this place. Okay, what will happen? This point, first of all, is going to only affect two other points, okay, at each time section. So for t equals to a over 2c, where is the original? Where does the zero? Where is the zero? You see, that means that this point is going down, right, and this point is also going down, right? So which means that this point is going down and this point is going down. So the initial perturbation at the origin at 0, okay, is now affecting these 2 points, but nowhere else, right? Nowhere else, only these 2 points. And the following effect will be at this point and at this point, because these two triangles are going down, right? These two triangles are going down. And same reason, this triangle is going down, this triangle is going down. So it's good. It's only affecting 2 points. So you have a question? Okay. See, it's always only affecting two points. Okay, so that's good. And if y, so and what about the initial perturbation for phi x0? Sorry, for psi x0. If I have a perturbation for the initial velocity, if I have an initial perturbation for the if I have a perturbation for the initial velocity, then it would affect my u whenever my x0 lies within x minus ct to x plus ct. Right? What is the range of x minus ct and x plus ct? What is the initial range of x minus ct and x plus ct? So you see, this line, okay, this line is exactly the line for x minus ct, okay, equals to x0, right? This line is exactly the line for x plus ct equals to x0. So for any x0 between these two, so for any x0 between x plus or minus ct, it should be the range over here, right? It should be exactly the range between these two lines. It should be exactly the range between these two lines. So that is to say, if I let's go back to our original target, right? You see, if at x0 at the initial condition, if I am perturbing the initial position at x0, it's only going to perturb the solutions on these two lines, exactly 2 points at a time section. But if I am perturbing the initial speed, if I'm perturbing the initial speed at x0, that means that I'm going to change the integration as long as the integrand range x minus ct and x plus ct that includes x0, which should be exactly this line. So that means exactly that I am going to any perturbation of the initial velocity at this point is going to change the following solution whenever it is in this cone. Whatever it is in this cone. Should I repeat this statement? So okay, so first of all, if I'm changing phi x0, I'm only going to change whatever is on this line and whatever is on this line, and nowhere else. If I'm perturbing the initial speed at x0, through the changing of the integration, I am going to perturb or change the solutions, the following solutions, whenever it lies in within this cone, where the y-axis is the t and y-axis is the x. Okay, and you see, actually there is a reason that we are choosing c as our wave speed. Well, in physics, what do we usually use for c? Speed of light. Now imagine that because you see this is a wave equation, right? Light is an electromagnetic wave. Okay, so imagine this represents the wave equation for the light, and nothing can be faster than the light. What does that mean? That means that if something is happening over here, okay, then after some time t, whatever it can affect is exactly lies within a range of the distance, right? Whatever is happening over here, it has nothing to do. It has nothing to do with what's happening over here, or here, right? So when this wave equation is representing the light, this actually has a specific name that's called light cone. Light cone. Again, that means that an event taking place at 0, okay, what is the range of the following events, or what's the range of the causality that it can affect? Okay, in the following time. Okay, so that's good. So this is a specific application in the physics. And one more thing that I would like to address. So I don't have time for energy, but it's actually very straightforward, and I'm going to need it for the next class. But another thing is that, okay, another question to raise the causality issue is that, let's say I am having, okay, let's say I'm looking into exactly at a solution, at a point, let's say this is my t, this is my x, okay? And I am exactly looking into the solution of uxt at this point, okay? So the question is, what can I manipulate in the initial conditions? Within the initial conditions, what can I manipulate to affect the value of uxt over here? What can I manipulate? Again, we can draw, what should we draw? The first, the two characteristic lines, right? I need to find a characteristic line that goes through this point, and another characteristic line goes through this point. Okay, this is my uxt, and it won't be very hard to compute what is this value and this value, which is the intersection, the two intersection points to the x-axis. Okay. You see, don't forget. This is my uxt, right? My uxt actually we have an explicit formula for that. My uxt equals to the sum, the average of phi evaluated at here and at here, right? And second, it equals to it also equals to whatever it is between this place. Whatever, it is also affected by the integration of the initial speed in this interval, right? So that means that if I would like to manipulate the solution at uxt, okay, I just need to manipulate whatever it is in this inverse cycle, in the inverse column over here. Okay, if I am doing something over here, it has nothing to do with my uxt because it's not fast enough. It's not fast enough to get to this place. Okay, if I'm manipulating anything that's over here, okay, it's not fast enough to get to this place. Okay? So whatever I need to do is that I'm going to manipulate this range. Okay? I'm going to manipulate this range, okay? So that I could manipulate my function vector, my solution vector for the next this range. Okay? So this is indeed a very interesting interpretation for the wave equation, and so there's no more for today. And the next class is going to be mostly on the diffusion equation, but we are first going to discuss the energy part for the wave equation. That's it. Thank you for coming.